Okay, good morning. Can everybody hear me, right? Yeah, I guess so. Okay, thank you, Melanie, for the introduction. Good morning, everyone. I know I'm the last thing between you and lunch, so I'll try to keep it light. My name is Lucas. I work for Booking.com. I believe I am a pragmatic data scientist. And today, what I would like to do is to just share with you some tricks and tools that I learned in my experience. I've been in the industry for many years already, and I work with many people. Most of them are better than me, so I learned a lot from them. And I would like to share these tricks, and I really hope that you guys like these tricks, that you can use them in your own projects, and maybe you can come up with your own tools and tricks. Maybe even find some mistakes in my own tricks. That would be awesome, because that way I will learn a bit. So let's get started. The first trick I would like to talk about is called KNN, from slow to fast, thanks to math. And the idea is that you use this trick whenever you are solving a k-nearest neighbor problem. So not sure if everybody is aware of what this problem is about, but just for the sake of argument, let's say that we have a set of documents. These are text documents. And we want to compute the most similar documents to every document in the data set. So usually the way you solve this problem is you somehow come up with the feature vector for every document. And this feature vector is usually built using the bag-of-force model. So for every document, you will have a feature vector, the length of the vocabulary of your data set. And every component in the vector will be the count of the words in that particular document. And this trick will only work if you want to use cosine similarity. Now, of course, there are many similarity functions that you can use, but usually cosine similarity is a very good choice. And it's very important to note that the choice of the similarity function has to be done with respect to the data and not to any other aspect. So if you want to use cosine similarity, how do you solve this problem? Well, the straightforward solution is to just compute all the feature vectors for your documents, and then whenever you need to compute the k-nearest neighbor for a particular document X, you just compute the cosine distance from X to every document, sort, and keep the last k elements if you sorted by similarity ascending. OK, that's a very good solution because it works. But if you take a closer look, we can analyze the computational complexity of this solution. And we can see that there are two parts in this algorithm. First, the easy part is when you sort. This will be n log n, because sorting. And n is, of course, the amount of objects in your database. But before sorting, you have to compute the similarity against all the possible documents. And that will be, in principle, linear. But of course, you have to take into account that every time you compute the similarity, you add a factor d, which is the dimension of your feature vector, which will be the length of your vocabulary in this case. So the total complexity will be something that grows like n log n plus something that grows like nd. And the thing is that usually log n will be much bigger than d. Suppose that you have 10 million documents, then the logarithm will be something like 7. But d will be for sure, I don't know, 10,000. So that's why, in general, we say that this algorithm is linear in both n and d. Now, of course, if you do computational complexity analysis, you want to ask the question, can we do better? And the usual ways to improve this algorithm is probably using a heap or maybe a quick select. But none of this will help because they will actually add some overhead. Now, the third way to solve this, to improve this, is to use a space partitioning tree. And that's where I want to focus on. The space partitioning tree will work as an index where you put your documents in the tree. And then whenever you want to compute the k-nearest neighbors, say, to a document X, you just read from the index. And the space partitioning tree will make it in logarithmic time, usually. But the problem is that we want to use cosine similarity. And cosine similarity is not a metric, because it doesn't hold the triangle inequality. And this is very bad news, because that means we cannot use space partitioning trees. At least the ones I know, they all require your distance function to be a metric. So that's not good. So, but here's some math that we can try to use to improve this or solve this problem. So this is not a proof, it's sort of a sketch, and there are two properties that we're going to use. One is that cosine distance is invariant under normalization. And what that means is very simple. If you have two vectors, A and B, you compute the cosine distance, say you get 0.5. Now if you normalize A and normalize B, and you compute the cosine distance of the normalized versions, you still get 0.5. The number doesn't change under normalization, because that's exactly what cosine will do with first normalize the vectors. So that's pretty simple. The second property is a little bit more opaque. And it says that if A and B are unit vectors, then the Euclidean distance will be exactly 2 minus 2 cosine between A and B. So this is not that easy to see. You can look up in the wiki the proof. But what I want to focus is the fact that you can already see that we are trying to sort of relate cosine similarity to Euclidean distance. And that's exactly what the third line says, is that if x is closer to A, is more similar to A than to B in the cosine space, then the normalized version of x will be closer to the normalized version of A than to the normalized version of B. I know this is a little bit tongue twister, but bear with me. So the idea of the trick is to exploit this lemma here to actually end up using a space partitioning tree. So here's the trick. Just normalize all your feature vectors, and whenever, of course, you build a space partitioning tree, for example, a KD tree, you put all the documents in the KD tree using Euclidean distance. Remember that we want to use cosine, but once we normalize the vector, we can use Euclidean, which is a proper metric, so all good with the KD trees. And whenever we want to compute the k-nearest neighbors to x, we just normalize x, and look up the KNN from the tree. And this will be logarithmic, which is awesome and much better than linear. So I don't want you guys to be convinced by just all this math. So what I did is I wrote some code and ran some experiments. And this wouldn't be a machine learning talk without the MNIST dataset in one slide at least. So for the ones that don't know, this dataset is just some handwritten digits, 70,000 pictures, 28 by 28 pixels, and the pixels go from 0 to 255. So this is a 4. And this is how the cosine similarity works. So the first column are the input pictures, and all the other columns are the most similar to the first in the same row. So in the first row, you see many 4s and a 9, so there is a mistake there. And the second row, you can see something. I think it's a 2, this thing here. Honestly, I don't know. But the algorithm believes it's an 8, and then a 7, and then the 9, so it's sort of confused. Which makes sense, because come on, if this is a 2, I don't know. But then it doesn't make more mistakes. All 8s, all 3s, all 5s, all 2s. And you can see that it doesn't only hit the actual number, but it also captures some similarities in the way the number is written. For instance, the 2, all of them has this loop. And there are many 2s which are more like a seat, but you don't see any of those there. So it's actually sort of computing similarly written, not only the same digit. So this is just to sort of justify why I decided to use cosine, and also to show that you can sort of impress people without using deep learning. And so here's the code I wrote. This experiment that I designed, which is very simple. I use sklearn, my favorite tool for machine learning, and very nice implementation of. I'm not saying that because Andres is here. No. So you can use the nearest neighbor implementation. And in the first version, I use metric equals cosine. But this is very funny, because cosine is not a metric. So, but you need to use, of course, brute force, because that's the only thing you can do. If you try to pass val tree or KD tree here, it will blow up. So that makes sense. Versus another version, which is the trick version, where I just normalize all my data set first. And then I use Euclidean with the ball tree, which is one particular space partitioning tree. And now I want to stress this. These two solutions are exactly the same. There isn't any approximation. So this is computed with both solutions. And this is very important because usually for getting some scale-up factors, you have to pay with accuracy. That's not the case for this trick. So results. On the x-axis, you can see the dataset size, which ranges from 5,000 to 40,000. And on the y-axis, you can see how long it took to compute the top 10 or top 9 most similar pictures for 20 pictures. So there are two things to note in this chart. First of all, the blue line is not tricky at all, so cosine and brute force. The green line is a space partition tree, particularly the KD tree, and the red one is the ball tree. Okay, so there are 2 or 3 things to note here. One is that the blue line is a straight line. So that sort of supports our hypothesis that the complexity of the problem is linear in n, which is important, right? Experiments validating what we computed using math. And the second thing to note is, of course, that both space partitioning trees are much better than the full scan solution. And the third thing to know maybe is that KD tree is a little bit worse than ball tree. Honestly, I'm not sure why, because the dimensionality of this dataset is not big, so it shouldn't be a problem. So I was actually expecting similar performance. But okay, it still beats the full scan, which is very good. So that's all. That's the first trick. Moving on to the second. Classification. To bad data, good math. So this trick, you can use it whenever you have a classifier and there are missing features in your at prediction time. So specifically, you have a classifier that predicts the probability of a class conditioned on a set of features. You train this classifier, all good. But then at prediction time, there are missing features. And an example of this in booking, for example, not everybody tell us whether they are doing a leisure or business trip. And then we like to train our models using only people that told us what kind of trip they are making. But then with this trained model, at prediction time, we don't know. And we still need to make a prediction. We still want to recommend hotels. So this is pretty frequent. And of course, there are many ways to solve this problem. The more usual maybe is to use the most common value, the most frequent value for that particular feature. You can use the expected value. You can use this average in some neighborhood, so similar people, do they do work or leisure, and so on and so forth. And you can go all the way to end up building a machine learning algorithm itself that will predict that particular value. But remember, that wasn't your initial goal. So you may want to think about it. So let's look at this a little bit closer. First of all these solutions try to predict the value that that's missing, right? There's nothing wrong with this, but this is just an observation about the most usual approach. Actually many of them are not applicable for categorical data. What is the average between business and leisure? I don't know. Other solutions are very particular to specific problems, like using the average in the neighborhood. This is very useful sometimes for pictures, for image, but in general it's not applicable. And finally, most of them are too naive, too simplistic, or they take a long time or an effort to build, like building a machine learning algorithm. And also, if you can build a machine learning algorithm that predicts this feature, then maybe you're better off using this technology to improve your current classifier. So this is the analysis I made about this problem. But I would like to propose a different way to look at this problem, which I call reductionism. And the idea of reductionism in the machine learning field is to simply express a problem in terms of problems that we know very well already. So in this case, the reductionist approach to this problem, I will simplify it to only 3 features. So you have a classifier that outputs the probability of a class given a feature A, B, and C. This we already have. It's a classifier that works. We already trained it. It's awesome. But now we have the problem to compute the probability of the class given only feature A and C, feature B is missing. So we want to reduce this problem that we don't know how to solve to this other problem that we already solved. And that's the approach that I propose. And for that, we need some math. Not rocket science. I hope you guys are familiar with the law of total probability, which allows us to express the probability of a random variable as a marginalization over some other random variable of our choice. But maybe not everybody will be that familiar with the law of total conditional probability, which is sort of the same, but we condition on C. Right? So the first law is very straightforward. There's nothing obscure going on here. But the second is not like that, because you have to assume that the random variables B and C are independent. And this may be a very strong assumption. But this equation here is what we're going to try to use to solve the reduction. So here's the trick. It's very simple. So we have the classifier already that outputs the probability given of a class given a feature A, B, and C. There might be some examples where feature B is missing, is not specified. And then in the trick, we assume that feature A, B, and C, they are all independent. Actually, for this particular case, we only need to assume that feature B is independent from feature A and C. And then we estimate this probability, which is the problem that we want to solve, using this equation that only needs this probability that we already know how to compute. And of course, it will need this other probability that is very easy to estimate from data. So this is the trick, and I know it's a little bit abstract, so here's an example. So suppose that we want to compute the probability of someone being happy going from one place to another for a purpose. Now, the purpose can be work or vacation, and sometimes it will be missing. Now, when we apply the trick, we assume that the purpose is independent from the source and the destination, which is sort of OK, I guess, right? You can go from anywhere to anywhere for both vacation and working. Then the idea is that you can estimate. So our problem is this: estimate this probability. How likely is that someone will be happy going from Paris to Tokyo? And for that, we're going to use the classifier that we already have that gives us the probability of being happy, condition on Paris, Tokyo, and work, weighted by the probability of work, plus the same for vacation. So in this example, all we're doing is estimating this probability using the model that we already built. And I think this is indeed very pragmatic, because you can build one single classifier and then use it whenever you want, for independently of how many or what features you're missing. OK, once again, I don't want to convince you with math in slides, so I wrote some code and ran some experiments. Again, handwritten digits. But this time, this is a smaller problem. Then you may tell me why, if you want. We have only 64 pixels this time. 70 possible values, not 250 like the MNIST dataset. And you will see that it's a quite extreme case already. So here's the procedure to show that this actually works. I split the dataset into train and test. So I have some pictures in the training data, in the training set, sorry, and some pictures on the test set. Then I train a multi-class logistic regression on the training set using all possible pixels, all the 64, no missing data. And then I randomly remove the pixels, 1, 2, 3, 4, from the pictures in the test set only. And then I use the already trained logistic regression on the train set to try to predict the contaminated test set. And I compare different approaches. So here are this is a picture. Yeah, I think this is a 2 or an 8. I don't know. Resolution is really low. But the dark blue squares are like the background. The light blue squares are the ink. And the red ones are the things that I removed. Are 3 pixels removed there. So here are the results. On the x-axis, you have how many pixels were removed from the test set. On the y-axis is the classification accuracy. This is a pretty balanced data set, so accuracy is a fair metric. And there are 5 lines. The black line is the baseline. So that one is actually tested against a test set that is not contaminated at all. So that's the best you can do with that particular classifier that you already trained. The blue line, which is the worst, is when you completely ignore the problem. You just don't know that there are missing features, and that's what happens. It degrades pretty fast. The red is when you fill in every pixel with the most likely value for that particular pixel. And the cyan, which is this one, it's when you use the average, which is sort of similar. Now, the green is the trick. And as you can see, it consistently improves over all the other. Why
is the black line?
Yeah. Because I train, the test and training sets are different for every 1, 2, 3. Yeah.
Then you can't compare them, right?
Why not? They're random, right?
Yeah. So you could just be looking at noise, right?
Yeah, I mean, this is not a paper-like presentation, right? So, of course, what I should do is sample many times and probably draw. I mean, the actual complaint will be there are not error bars. Yeah, there aren't. Okay. So those are the results I got. I run this many times and I always get consistently. The code is available, so if you want to wait sort of 3 days to get these confidence intervals built, because you can imagine that this sum is over all the possible combinations of all the missing features, and that's the catch with this trick. But we can discuss later. Okay. Anyway, I think it's still a very valid approach to try, because it will save you a lot of work. You just use a very simple equation to solve a problem that you didn't have with a solution that you already have. So that's about it for this one. And I have a last one, which is about discretization. It's all in the head. So the problem, this one is a little bit looser. So we have data, we have feature values, and some particular values. We want to sort of group them into some bins or clusters of groups. So for example, a usual case is the age of a person. So you have 1 million of records of people, and you have ages from 0 to 110, right? I don't know anybody living more than that. So maybe you want to sort of group these ages, because you believe that if someone has 0, 1, or 2 years, it's not the same. They're growing, they're going from being a baby to a child, whereas if they have 73, 74, 75, it's sort of the same. So you want to find these groups of scalars, and this is also known as discretization, binning, quantization, 1D clustering, you name it, right? Solutions are many. I just name a few here. Quantile binning is probably the most usual, where you just take standard deviations or percentiles. Jenks natural breaks is also sort of popular. It turns out that it's exactly the same as doing k-means, which is a very popular clustering algorithm for one-dimensional data. And then you have supervised methods, which are very, very interesting. But these supervised methods is when you find these groups for a particular task. For instance, you're solving a classification task, and you use a random forest or decision trees. Then the decision tree will try to find the groups of ages, for example, that maximize the probability of predicting the class correctly. So these are 3 sort of kind of solutions. So one thing we can say about this is that many methods will take the amount of clusters as an input. And this is very annoying sometimes, because I have ages of people. Just I don't know how many groups there will be. So this is usually a problem. A second observation is supervised methods are only suitable for one specific task. And sometimes it's very funny, because you will find stuff like, people with 34 years old, they behave exactly the same as someone with 16. Okay. But that's because the data, this group, helps to solve a particular task. But then these groups, you cannot use them to understand your problem better, or to talk to people, or to port this to some other problem. And also, most methods are not very robust to different distribution types. Actually, most of these methods will assume that your data is pretty symmetric. If you have some skew in your data set, these methods won't work very well. So what can we do? Well, let's talk about heavy tail data. And it's very difficult to express or define or find a definition to heavy tail data. So I came up with some examples. The most common ones are, for example, the power law, where a variable is related to another one, x, as a geometric function. The Pareto distribution is the same, but here the variable is particularly the probability density of x. And then here's my favorite, which is the rank size function, where the value is actually a power law with respect to its rank in the list. So if you take all the ages of all the persons and you sort them by age, of course, and then you plot age against the rank in the list, then you get a power law. And then the log normal distribution, which has nothing to do with power laws at all, but it's also a heavy tail distribution. Now, there is a very nice property of heavy tail distribution, which is that the mean, which is usually not very informative, right? If you have a power law distribution, the mean won't tell you anything. It's not a very good centrality estimator of the data. But it's very interesting that you can use the mean to separate the values between head and tail. So we're going to use this fact, this property of heavy tail data, to come up with the means. And the best way I managed to explain this is with, there's an example of heavy tail data here, which is probably you have already seen. This is the population of US cities in 2009. So the x-axis is the rank in the population rank of every particular city. And in the y-axis is the population, how many people live there. The blue line is exactly this, and the red line is the average. So you can see that all these cities are above the average, but all these others are not. So this is sort of an illustration of this principle where the mean is splitting the data into head and tail. There are only 52 cities above the average, and about 2010, I think, below the average. And this is very funny because this is exactly 2179, which is very close to Pareto rule. So this is an illustration of this principle, and here's how we're going to use the trick. So yeah, the best way to explain this trick is with some code. So you have data, say a list of ages, and this is a list of recs that we're going to return. So n is just how many data points we have, and then we compute the head as all the values that are above the mean. Then we have the tail, which are all the values that are below or equal to the mean. And then we append the mean of the data to the breaks. Yeah, I know, I'm computing the mean many times, but I just thought that it was more readable like this. Now, if the length of the head is less than 40% of the total data set, then that means that there is still a heavy tail data, and we continue doing this on the head. So this is a recursive call to the head, keeping the list of breaks. And we continue like that until this condition is no longer met, which means the data now is symmetric, and then we're done. That's it. So this is an algorithm that you can use to compute bins on heavy tail data. Now, again, to convince you that this is useful somehow, even without confidence intervals, I designed this experiment in which I used the Boston housing dataset from UCI. This dataset has houses with features and the price, and the task is to predict the price of the house. I use linear regression as a baseline. Then I apply head-tail breaks to every feature because they are all continuous, real value features. And then I discretize them using the bins that I got from the head-tail breaks trick. And then I one-hot encode these bins. And finally, I use this in the regression as a non-linear feature. So this is what the algorithm found. This is one of the features that best worked, which is not very nice to talk about, but which is per capita crime rate by town. So luckily, there are not many houses located at places where the crime is high, just a few. But there are plenty where the crime is low. Now, if you are little bit strict, this is actually a head, torso, tail, because there is also pretty dense in the middle. But the algorithm actually works anyway, because it's pretty robust to this condition. And these are the bins that it found. So I hope you can see the red line. Yeah, it's pretty clear, actually, which is the actual data. And then these are the bins. So everything between 0 and 3 is one category. Everything between 359. Everything from 359 to 13 is also a category, and so on and so forth. This limit is not found by the algorithm. I put it myself to build the histogram, but it will never. I mean, the algorithm finds this first, then this, and finally the 0. And the blue squares are a histogram of how many data points are in every bin. So one interesting thing to note here is that if I can tell you that the red line is actually a smoothed version of the histogram. But this is not true. The red line is the actual data. So it's very funny to see how this algorithm is sort of doing the inverse of smoothing. And I think that's a signal that the algorithm will actually find very useful bins. And it's also very important to note that the amount of bins is given as a response by the algorithm. It's not the input. So I didn't put a slide, but I did this for every feature, and it found about 4 features which have this same distribution, and it improved the score, the RMSE score, by 6%, more or less. And of course, the reason is that we are adding non-linearities. So the algorithm is linear, but if you add this binning, then you get some non-linearities. So that's about it for tricks. I just wanted to say a few words about Pragmatic Data Scientist. This talk, I presented 3 tricks, but this talk is about pragmatic data science. And if you want to become a pragmatic data scientist, my recipe is to get 3 basic skills: math, computer science, and machine learning. You cannot skip any of these if you want to be a pragmatic data scientist. And some values, which are experimentation, like I show in the talk. Everything I spoke about is sort of at least represented by experiments. And it's one of my values that one experiment is worth 1,000 equations. You can write as many equations as you want, but if you have one successful experiment, that's when you actually make a step forward. And criticism is also a very important value. I don't know if you are familiar with the no-free-lunch theorem, that it says that for every algorithm, if it works very well in one specific regime, in one specific condition, for sure there's another condition for which will work really bad. And that means that you have to be very careful with these tricks, because for every trick, there is a trap. And I didn't put the traps here on purpose to see if we can talk about them later on and see if you can find what are the traps for every trick I expose here. I challenge you guys. I think he found one already. And finally, another value that I propose is reductionism. I think this is very important to reduce new problems to very well-known and studied problems. And this is a very philosophical, of course, thing, but there is actually a machine learning field called reductionism. And I think John Lamford, which is the main contributor of Vopal-Wabbit, is one of the main researchers in this area. And Vopal-Wabbit in itself is using a lot of reductionism to solve the problems. And I think this is a very interesting approach to engineering and data science. And I think these 6 things are key elements to be a pragmatic data scientist. That's all. I want to thank Themis Mavridis here for helping me with the code. Also, Pablo Steveros, he's not around. Melanie Mueller for helping me with the slides also. And also these tricks and some more are available in my GitHub in that URL. Please don't look at the other projects, are not very good. That's all I have, guys. Thanks.
Questions?
Hi, thank you very much for the talk. It was really useful.
I was thinking on the second trick when you were inputting the missing values.
Yeah.
I was thinking, yeah, this one. I was thinking in the digit recognition, you also have values that are missing. But in your problem, I was guessing like, I don't know, coming, for example, to this conference, is it leisure, is it work? I don't know if missing values could be considered a different category in this case. So I'm not sure if you check that, just assuming that it's like others more than
missing. I understand. Yeah, absolutely. That's a thing to look into, and it depends on every problem. A missing value is a missing value. If you really think there is information in the fact that the value is missing, then you should definitely use it as a feature. But this you should check beforehand, right? So when you build the classifier, you will check correlation between the no value and the class, or whatever output you want to predict. And if this no value helps you with the classifier, then you should keep it. But if it doesn't, you shouldn't keep it. You should remove it. And then if you remove it, then in prediction time, you don't have this capability, right? So if you keep it only to be able to make a prediction, you actually hurting your algorithm just to be able to make a prediction when the value is missing. So you should only keep the no value when that actually adds information to your predictor.
Hi, thanks for the talk.
Sure.
About your first trick, the one about normalization and closing.
Yeah.
Is this for using cases when you have the vector somehow pre-normalized? Because from what I see, you have to normalize n vectors of dimension d.
Yeah.
So the normalization phase is O of nd, I think.
Oh yes, of course. So yeah, that's a good catch. That's part of the traps. When you fit the model, I didn't put here. Themis wanted me to put this slide. When you fit the model, sorry, where is it? Here. This does nothing, right? But this one will build the KD tree, and this will take a lot of time. So you pay the cost at the beginning, but only once. So that's up to you whether this is depends on the problem. Yeah. Yeah, but that's definitely a trap.
So for the second trick in your application, is the independence assumption actually true?
I didn't check. I don't think so.
Yeah, I would imagine that like more people go to work to like a big city and to the beach for a holiday or something like that.
For that particular, you mean?
Yeah.
Oh, yeah. No, that's for sure not. Yeah, we know
Yeah.
for sure not. Yeah.
So, but then one way around the independence assumption would be to sort of not impute the label, but build a probability model, right? You can like train a model, like a logistic regression or whatever, to get the distribution, the conditional distributions, and that it probably would work better, right?
Yeah, that was something like this. Yeah. Indeed.
I mean, not to predict the missing feature,
but you use the probability. You use the probability as a feature.
Exactly.
Yeah, yeah. That's I should have probably done that. But for that, you need to build a new classifier. And what if you have missing values on that fucking? So if you start doing that, you end up building a neural network by hand, right? Probabilities, layers, probabilities. But it is absolutely a good approach. This is just a very general approach. This is my point with this.
No,
okay.
No. I want to do the same sum. Go to the next slide.
Oh, okay. Okay, I didn't get it then. Yeah.
This one, I want to build a classifier that predicts PR of B given BI given C, and I built like a logistic regression.
If you condition here, you're breaking everything, right?
No.
Oh no, you're right. You're right.
No,
I understand.
You left out the conditioning, and I do the conditioning.
Yeah.
I built a model for the conditional probability.
Yeah. Yours is more general than mine, but you didn't build it. Thought experiments don't have results, remember. No, but it's of course a very good, it's a very good. So you guys, I hope you guys follow. So we are conditioning everything on C, and here I should also condition on C, but I drop it using this independence assumption. So what Andrea says is, rather than doing that, we just keep the conditioning, and then we build another machine learning to predict, to compute, or it will be an estimator of that particular probability. That's indeed a very good idea.
More questions? Someone wants to point out another trap? Okay, let's thank Lucas again.